Angular momentum is analogous to linear momentum. And one reason why this analogy is so strong is that angular momentum is a conserved quantity, just like linear momentum. If you remember, in the linear momentum, when no external force is applied to the system, the change in momentum of the system is zero. So the momentum is the same before and after any complicated interaction between any system of particles. The same thing happens with torque. If we have a spinning system and no external torque is applied to our system, then the angular momentum is the same before and after any complicated process occurs. As long as there's no torque, there's no change in the angular momentum. So the angular momentum is the angular velocity, omega, times the moment of inertia, I. That means that there are two types of conservation of angular momentum problems that we can envision. One would be when the moment of inertia of an object changes. So in linear momentum, the mass of an object is fixed, and at least in classical mechanics, so that's not going to change. But in angular momentum, if we change the position of the mass with respect to the axis of rotation, the moment of inertia can change, even if we do not apply a torque. The classic example of this is a figure skater who, as they spin around, first they start out with their arms out, and then as they pull their arms in, they spin faster and faster because they have reduced their moment of inertia by pulling the weight of their arms in, and so due to conservation of angular momentum, their angular velocity has to increase because the product of those two things is a constant. The other type of question we can solve with this is collisions. So I think the one we'll do here is we're dropping a rotating disk onto another, or the other examples if we jump onto like a spinning Ferris wheel, and then we can solve this using conservation of angular momentum. So now we're going to look at an example similar to the figure skater example I just mentioned. A person here is spinning around, and they take some masses and hold them out, and then they pull the weights closer to themselves. So as the person pulls their weights in, they are not applying a torque because they're pulling them directly along the radius. So the angle is 180 degrees, so the torque here is zero. If there is no external torque, then the angular momentum must be conserved. So we use our right-hand rule to find the direction of the angular velocity. So our finger wraps around the rotational axis, and our thumb points down, so the angular momentum points down. And the angular velocity points down as well. Because there is no torque done to the person, the final angular momentum is the same as the initial. However, their moment of inertia is smaller because the weights are closer to their body, so the r value, the radius value, is smaller. So if I is smaller, then omega must be larger, and so they're going to spin around faster. If we want to do this more quantitatively, then the initial and final angular momentum are equal to each other. So L initial is equal to L final. The angular momentum is the angular velocity times the moment of inertia, and the moment of inertia is changing here. So the initial moment of inertia times the initial angular velocity is equal to the final moment of inertia times the final angular velocity. To solve for the final angular velocity, we isolate it by dividing both sides by the final moment of inertia. So if we know the change in the moment of inertia, we know the change in the angular velocity. Also notice if your final moment of inertia is smaller than your initial, then that means that the angular velocity increases, and if the reverse, if the final moment of inertia is larger, then your angular velocity is smaller. The next type of problem we can solve using the conservation of angular momentum is a collision between two spinning objects. So usually what we mean is that two spinning objects are dropped on top of each other, or someone runs and jumps onto a spinning object. But for the problem here, we have two spinning objects, a spinning disk and a spinning ring. The ring has a mass of 2m and is spinning clockwise with an angular velocity of 2 omega, and the disk is rotating in the opposite direction, counterclockwise, with an angular velocity of 4 omega. So what is the angular velocity after they've been dropped on top of each other? Well, to find this, we find the angular momentum of the ring and the disk each before we collide, and then we add them together to get the total angular momentum. So first, let's do the ring. The mass is 2m, so the moment of inertia of a ring is mr squared. So the moment of inertia is 2m times r squared. The angular velocity is 2 omega, but it is clockwise. So the angular velocity vector points down, if you do your right-hand rule, so it is negative 2 omega. That means that the final moment is 2 mr squared times negative 2 omega. So our angular momentum of the ring here is a negative 4 mr squared. For the disk, the mass is m and the angular velocity is 4 omega, this time in the counterclockwise direction. So the moment of inertia of a disk is 1/2 mr squared. So the moment of inertia is 1/2 mr squared, and the angular velocity is 4 omega, which is counterclockwise, so the angular velocity vector points up, and it's positive. So it's 1/2 mr squared times 4 gives us 2 mr squared omega. Okay. So, all right, there it is. And so then we add them all together, so we get the negative 4 mr squared omega from the ring and the 2 mr squared omega from the disk, and we add them together to get a negative 2 mr squared omega. So now we want to find the final angular velocity in terms of the initial angular velocity. The moment of inertia is the combined moment of inertia of the ring and the disk. So it's 2 mr squared plus 1/2 mr squared, so the total is 2.5 mr squared, or 5/2 mr squared. That times the final angular velocity is then the final angular momentum. The final and initial angular momentum are equal to each other, so this is due to the conservation of angular momentum. So the 5/2 mr squared times the final angular velocity is equal to the negative 2 mr squared omega initial. We can then solve this, and if we do this, we find that the final omega, the final angular velocity, is a negative 4/5 omega initial. So the idea is that if you find the angular momentum before the collision by adding up the angular momentum of the ring and the disk, and then the final angular momentum is the total moment of inertia, the sum of the two times the final angular velocity. So we then solve for that final angular velocity. This is a lot like the completely inelastic collision problems we did before. So we have two things with different momentum to start with. Then once they smash into each other, they're now moving together, and so then we can find the final momentum is the sum of the masses times the final velocity. Here it's the same thing, it's just we're using moment of inertia instead of the mass. Okay, so you have a problem like this to do, and good luck.